So a particle is oscillating in simple harmonic motion. It's about the origin. It says it's got a period of 24 seconds and amplitude 120 meters. And we know initially it's at the origin and it's got a positive velocity. So you can imagine we can use, sorry about that, the fact that we can use a sine curve where it's, so the period is 24. So that must be 12, 6, 18. This will be our x, this will be our t, because it started at the origin and had a positive velocity. So if I look at the gradient of the curve, it starts off as positive. And we could do something with velocity in a second as well. So if that's the case, we can already write down a function of x, displacement. We can use sine. So we've got sine, we've told the amplitude is 120 meters, so we know that's 120 there. And we know the period is 24. So remember, period is 2 pi on n. So we've got 24. So just rearranging that. So I'm timesing by n and dividing by 24. So I get pi on 12 there. So I know this must be pi t on 12. So nt. All right, and we know it starts at 0 at the origin, so plus 0. So that's the displacement function. What about velocity? Well, if we differentiate that with respect to time, you know that its sine is going to go to cos, and it's going to have the same angle, so pi t on 12. But I'm also timesing the 120 out the front by pi on 12. So if you think about it, I'm timesing 120 by pi on 12. So we are going to have 10 pi out the front. So that's our velocity there. And if I were to graph it, remember it's a cos curve. So here we go. Sorry about my graphs. So that's going to be, the amplitude is 10 pi, so it's going between 10 pi and minus 10 pi. So we've still got a period of 24, so that's 12, that's 18, that's 6. All right, there we go. So the next question says, so part of that question, state the maximum speed, not velocity, so speed, so we don't worry about direction. And you can see it would just come from either, your graph, which is the amplitude, or from your amplitude, from your function here. So we know that the max speed is 10 pi, and we're in meters per second. All right, so part B, what is the first time when it's 30 meters? So we're talking displacement, and we're looking to the right of the origin and then to the left of the origin. So if we look, so we know, and I didn't write it in, but we've got an amplitude of 120. So if we're looking for where it's 30 meters to the right, so we're looking somewhere here, 30 meters to the right, and 30 meters to the left of the origin, so we're looking here. All right, so how do we do that? Well, let's use our displacement equation first. So and let's set that to 30. So we've got 30 is 120 sine pi t on 12. So we're going to divide by 120. So 30 on 120 gives us a quarter. So we've got a quarter is sine pi t on 12. So how am I going to solve for t? Well, I have to inverse sine. So inverse sine of a quarter. And then I'm going to times 12 and divide by pi to get t as the subject. All right, and when you put that in the calculator, don't forget to use radians here. We're in radians. I'll just move that up a bit. All right, so we get 0.965167, etc. seconds. So to 4 significant figures, which is what it asks for, that will have to round to 2. So that many seconds, and that's to 4 sig figs. All right, so that's the first time, that's what we'd expect. So it's pretty close to right at the beginning. The other time, if we look at our picture, is sometime after 12 seconds, so just after 12 seconds. So really we could just add 12 seconds because it'll be the same number of seconds after the 0, same number of seconds after the 12. But if you didn't want to do it that way, think about where next our time, so if we're looking at back at the graph, this space here would be in the 3rd quadrant. Oops. So we're looking at the 3rd quadrant, and in the 3rd quadrant, go back to that, we've got t being, I'll just do it here, sorry, messy. So in the 3rd quadrant, we've got the angle, so here's the angle, plus pi, so that's the 3rd quadrant, right? And then again, I'll just rub that out for a little room. Again, so we're doing times 12 on pi. So when you put that in the calculator, you know we're going to get 12.9652. So it was 5167, etc. So to 4 sig figs, it would be 97 seconds. 4 sig figs. All right, please excuse the mess. Hopefully that helps you understand that a little better. Okay, so let's have a look then at the next part. So part C, find the first 2 times its speed is half its maximum speed. So we can see there that 10 pi is its maximum, and we're talking speed, so we don't care about direction. So, you know, if I'm looking for half of that, it's kind of going to happen there and here. Again, there'll be some symmetry here. So if we find one, we can use the graph or we can use our algebra. Okay, so let me just rub that out so we've got a bit more room. All right, so using our velocity equation, we've got half is what we want. So half of 10 pi is 5 pi, 10 pi being max, so we're looking at where it's 5 pi. So you can think of it as using the velocity equation. We're looking for 5 pi for velocity in this equation, but that's really just the same as a half, 5 pi on 10 pi, so a half for this cos curve. All right, so let's look at the first time. So if we inverse cos of a half and times by 12 on pi, put that in the calculator, don't forget to be in radians, you get 4 seconds. So you can see if we look at 4 seconds, that's actually exactly halfway here. So you can tell the next one will be 8 seconds. So from the graph, or if you think about it, we're looking for a negative 5 pi. So if you think of negative 5 pi there, we're going to get a negative a half. So if we do the same thing that we did before, but this time do inverse cos of negative a half, hopefully you put that in the calculator, you will get 8 seconds. Okay, hopefully that helped.